All right, so happy E-Day, everybody. We've got this angle. What's that? What's that letter there? Theta, right? Good. That's theta, and it's negative 6,789.1 degrees. We see the degrubble there. We want to find theta cot, which means we're trying to find the what? What's cot stand for? Coterminal angle. And then the E epsilon means within one rotation, between 0 degrees and 360 degrees. Okay, so let's do that. Since it's a negative angle, instead of just adding back 4 rotations, we'll expedite it by going negative 6,789.1. We'll divide by 360, right? That converts it to rotations. So that's negative 18 full rotations. There are 2 ways to do this, remember. Let me store this as X. You can either add back the 18, the integer that you see there, to get the decimal, and then remultiply by 360. And you get a coterminal angle, right? Negative 309. But we want it to be between 0 and 360. So I need to go 1 more rotation. So if I then just say plus 360, then I'll have the one I want. Okay. So theta cot is 50.9 degrees. So that's one way to do it. The other way to do it, when you divide by 360, if you see a negative number, and you know we want the angle between 0 and 360, the positive angle, you could just, instead of adding the rotation after you convert it back to degrees, you can add a rotation here. So instead of adding 18 back, I'll add 19 rotations back. And that gives me a positive fraction, which now when I multiply by 360 gives me the number that I want directly. So it doesn't matter when you add that full rotation back. If you start with a negative angle, you either add 360 to it after you convert it back to degrees, or you add 1 extra rotation when it's in rotation units. Okay. Now let's sketch that. 50.9, kind of a bad angle to choose, but an easy one, I should say, right? That's in quadrant 1. So that's not only the coterminal angle, that is also the reference angle. Yeah, there you go. They're the same. And then in DMS, I guess I can just say answer, second negative, and then I'll hit second apps, right? Angle, and go to number 4. Easy there, boy. Yeah, you can just press 4. And it's not as fun. 50 degrees, 54 minutes, and 0 seconds. If it's 0 seconds, you don't even have to write it. So 50, 54. It's kind of nice maybe to have it though, just so that you know it wasn't overlooked, but actually computed. So there you go. All right. Everyone warm now, right? Everyone's warm. Yeah, so the outcome of any serious research can only be to make 2 questions grow where only 1 grew before. Thank you for that awesome quote, Thorstein Veblen. Yeah, all right. Instead of putting motivational quotes at the very top, I think I'm going to start putting math quotes or math-related quotes like that one there. Maybe every once in a while I'll put just like a truly motivating quote, like you read it and like, wow. That could be, yeah, then they're one and the same. Kind of like in this case, the coterminal and the reference are one and the same, right? Yeah. All right. So let's go ahead and how much time do we got? 20 minutes, Brady? Okay. So let's put your calculators away. Not like back in the, but just like turn them off. We don't need them. See you later. We are going to learn a different way to measure rotation other than degree. Degrees work nicely. But there's a problem when you start doing computations that involve distances or lengths, okay? And that's important because you know from stoichiometry, dimensional analysis, that units have to be correct on a final answer. Otherwise, the answer makes no sense. And that's why when you strive to get the units you want, it's a way to verify that your calculations are correct. So the other way that we're going to call it is called a radian. And you probably have heard that, right? Radian. Now, radian, the word radian sounds a lot like what other word? Radius, right? And that is not a coincidence, right? Like the letter E, lowercase, being Euler's number, right? That's not a coincidence, as the guy in the video said. It's okay. Radian is built on a radius, okay? So let's see what a radian is. If you were to take a circle of any size, I have one drawn here, and you look at the length of the radius, which is called r here, okay? The radius of that circle, if we put the center of this circle at the origin, then I can rotate around. If you take that length of the radius and you start over here in standard position at this point on the circle, if you were to wrap that length of the radius around one length and stop, it would land right here. This would be one radius length around the curve, right? If you were to then draw a line back to the origin, the angle that subtends the arc, that's what we call that. When you go around the circle, we call that an arc, right? An arc length. We denote arc length by the letter S, and I'll tell you why S here in a little bit. But the arc length of one radius wrapped around any circle, when you draw the line back to the center, we call this the central angle. The angle that subtends, sub means below, right? So the angle that's below the arc, we say it has a measure of 1 radian. Okay, so theta is, theta in this case would be 1 radian. Or we abbreviate it 1 rad. Okay, now let's keep going. What if I took that length of the radius and wrapped it around twice? Well, this angle, I'm not going to draw the arc to it after this one because it gets a little bit messy, but that's going to be 2 radians. Okay, 2 radians, because it's the length of another radius. One length of the radius plus another length of a radius, boom, draw it back, you get 2 radians. If you go another length of the radius, you're going to end up with right here. There's another radius length. I'm just going to write this angle as 3 radians, 3 rads. Okay, and again, I have room for one more arc. There we go. So it's still in standard position. 3 lengths of the radius. So any circle, you wrap 3 lengths of the radius around its circumference, and you're going to fall just short of 180 degrees. All right, do it again. Take another length of the radius, wrap it around the arc, or the angle that goes all the way around in standard position and lands on that terminal ray. We call this another length of the radius, right? So we call this, how many radius lengths? 1, 2, 3. We call this 4 radians. Fun. Let's do it again. Another length of the radius would be about right here. So here's another radius. And where it goes all the way around, we call this 5 radians. And we do it again. And it lands about right there. Here's another length of the radius. And so we call the angle that almost goes all the way around, almost makes it all the way around, our 6 radians, RAD for short. Rad, right? Awesome. That was a movie in the 80s called Rad. The whole movie was about a guy on a bike, and the whole movie was him trying to do a single backflip on the bike, which had never been done, right? And now you see people do many backflips on bikes, but the movie was called Rad. So I think that movie every time I work with angles and radians. All right, so this is irrespective of size, by the way. If you had a bigger circle or a smaller circle, it would be proportional. So in other words, let's say that I had a circle that was a little bit bigger. Snap and center it. If I had a circle that was slightly larger, then of course now the radius is larger. Yes, the radius would be larger. Guess what? If I took that larger radius and wrapped it around its circumference, guess where it's going to land? Yeah, it's going to land it's going to land on that same terminal ray, because they're linear, they're proportional to each other. The scale factor divides out. So is 1 radian 60 degrees? Not quite, because if 1 radian were 60 degrees, then when we go 6 lengths all the way around, 6 radians would make it all the way back to x-axis. So it's a little bit less than 60 degrees, right? Because 6 lengths of a radius of any circle around its circumference always comes up a little bit short. We're a little bit less than a third short. There's about 0.28 of a radius a little less than a third of a radius left over. We'll just call it rads, okay? Now, that's kind of inconvenient, right? It would have been nice if it would have been perfectly 6 all the way around. Then 1 radian could have been 60 degrees, but that's not how the geometry plays itself out. The geometry, as you heard in the video, that E cannot be derived from geometry, pi can. All right, take any circle, any radius, wrap it around. You can always fit 6 of them plus a little bit less than a third of another one. So the question is then, how can we figure that out? What is that number? Well, turns out that we can figure it out pretty easily. Because of Archimedes, the guy hiding behind the balloons there, we know that the circumference of a circle is what? What's the formula for circumference of a circle? Y'all don't know the formula for the circumference? 2 pi r, or pi d, right? The area, I heard someone say pi r squared. The area of a circle is pi r squared. The circumference is 2 pi r, okay? And that was given to us by Archimedes. Archimedes discovered this formula by doing what's called reductio ad absurdum. It's kind of like the limit idea. You could see on the poster here. What he did is he ended up taking a circle and he found the perimeter of an inscribed 96-sided polygon. And that gave him a lower bound on pi, 3 10/70ths. And then he did a 96-sided polygon on the outside of the circle, and that gave him an upper bound for pi, which is 3 10/71. And that's pretty close. So Archimedes gave us these. Now, let's define what an arc length is, okay? An arc length, well, let's not even define an arc length. I want that to be a consequence of how we define it. Let's come down here, and before we get back to the circumference, let's define exactly what a radian is. It's in a box. We kind of understand what a radian is, right? It's an angle measure that's related to the radius. So a radian is officially the measure of the central angle of a circle. That's going to be the angle that we're always interested in. We call that a central angle because it's near the center. It's near the origin. Subtended by an arc. We know what that means too. Equal in length to the radius of the circle. So for any angle measure theta in standard position, we define it as the ratio of the arc length S to the radius R of the circle. Okay? Represented mathematically, here it is. This is a super important equation. The radian measure, theta in radians, is going to be the ratio of the arc length S, that's how far you travel around the circle, along the circumference, divided by the radius of the circle itself. Okay? Now, why do we use S for arc length? That's a good question. Again, it goes back to the ancient Greeks. The ancient Greeks used a unit of measure for length called the stadia. Instead of feet, instead of meters, they use stadia. And that's where the word stadium comes from, okay? FYI. And so because that's their unit of length, the first letter in stadia, of course, is S. And so that's why we use S. Eratosthenes, just on a side note, a mathematician named Eratosthenes was able to approximate the circumference of the Earth in stadia using the shadow that the sun casted in a well where he was at in Alexandria, and then at another well at the same time in Siena or whatever it was. So anyway, a lot of history in math. It's pretty fascinating. Real people came up with this. But we don't use A for arc length because A is already reserved for area, right? So we use stadia. So stadia is the arc length. So let's see now. Radian is the ratio of the arc to the radius. So look at this. If I went 2 lengths of the radius around, right, and I landed here, then the angle measure should be 2 lengths of the radius, would you agree? Divided by the radius itself, and I get what? 2 rads, okay? Now, what if I know the radius's size? What if the radius happens to be 5? Well, then theta in this case is going to be 2 lengths of the radius, so 2 times 5 divided by the radius, which is 5. Guess what? It divides out. See? Now, this is probably the most important aspect of a radian, why we need it. Radians are unitless. Super important. What are the units of a radian? Nothing, okay? Nothing. Why is that? Well, it comes directly from their definition. It's a ratio of two lengths. So we might be measuring the arc length in inches, and we would be measuring the radius also in the same length unit, inches. And guess what happens with the units? Don't say cancel. They what? They divide out. And that's why it's unitless, okay? Unitless. Very important, because when you start doing calculations that involve lengths or distances around rotated devices, degrees mess up the final units, whereas radians make the calculations work when you do dimensional analysis. All right. Now, typically when we write theta equals like 2 up here, we typically write rads behind it. But that's just to keep it in the context of an angle. If I just put theta equals 2, you might be thinking, is it 2 degrees or is it 2 feet, right? You kind of lose the context. So rad 2 bananas. So this is just a description. It's not a unit. So if you left it off your final answer, I wouldn't deduct points. But remember, the goal in this class is to communicate. And so putting rads behind it, which is the plural of radians, it's nice, okay? Now, if it follows theta and there's no degrubble, we can all assume it's supposed to be radians. That's why the degrubble is so important when you are wanting it to be degrees. All right, so here's the question. One rotation, we know, is 360 degrees, right? All the way around. We talked about why. But we also know one rotation now is approximately 6 point, and I gave you the number 28 radians, but you don't even know it's 28, let's say. You know it's going to be 6 full lengths of the radius around any circle plus a little bit left over. How can we find that? Decimal. Well, this is where we go back to the circumference. Thank you, Archimedes. The circumference of a circle is 2 pi r. Yes, yes? Thank you, Archimedes. Let's look at the formula now for theta. Theta is S over r. You got to memorize that. It's just the ratio of an arc length to a radius. Well, for one rotation, let's write this here. For one rotation, the arc length S is equal to what? If you go all the way around. What do we call the arc length when we actually go all the way around? It's called the what? It rhymes with circumference. Yeah, circumference. Yeah. So for one full rotation, S is equal to C. So I can use substitution into Archimedes' formula. So what does that mean? Theta, which is the radian measure now, the radian measure for one rotation, bless you, is equal to not just S over R, but what? C over R. Everyone okay with that? Now let's substitute. C, we know, is 2 pi r. Thank you, Archimedes, divided by r. And guess what happens with your RDRRs? They divide out, and we're left with, oh my gosh, 2 pi radians. And we just came up with a conversion factor. 360 degrees is equal to 2 pi radians. Now, of course, you know pi is about 3.14. So 2 pi is approximately 6 point what? 28. That's where I got that. Now, here is a conversion factor. But guess what? We can simplify that conversion factor. They're both even, right? So if I divide both sides by 2, I get 180 degrees is equal to what? Pi rads. And that's the simplified version. So that's going to be our conversion, right? Now, pi is an irrational number, but what does that mean? Never forget what a radian is. A radian is the length the radian measure of an angle is how many radiuses you can get around in relation to the radius. So if I have the radius of 1 unit, there's 1, 2, 3, and then this little piece left over is 0.14, right? So we now have these two conversion factors. We have 180 degrees over pi radians, and we have pi radians over 180 degrees. These are our conversion factors. Now, it's going to become quite important for us to just know flat out that half a rotation is pi. All right, a full rotation is 2 pi, not 1 pi. So let's go ahead and divide this around. This will be the last thing we do today. In degrees, I have 0 degrees, I have 180 degrees, I have 90 degrees, and then I have 270 degrees, and then I have 360 degrees. Let's go ahead and put the radian equivalence next to them. I'll use a different color. This is also 0 radians, and here's how we could partition it. 180 degrees, we just said is pi radians, didn't we? And now look what we can come up here. 90 degrees is going to be half of 180. So what's half of pi? We just call it pi halves. Instead of 1/2 times pi, we call it pi divided by 2. Once we have that, once we have our quarter cycle counting interval, we can start counting by multiples of 90, right? 90, 180, 270, 360. We just keep adding 90 plus 90 plus 90. Well, now we know that in radians. So every time we go to another axis, we just add pi halves. Let's try it. 0 plus pi halves is pi halves. What's pi halves plus pi halves? Yeah, 2 pi halves or pi. What is 2 pi halves plus 1 pi half? 3 pi halves or 1.5 pi. And then what's 3 pi halves plus another pi halves? 4 pi halves, also known as 2 pi. Okay, it's actually easier to count in multiples of pi than it is with numbers, right? Because what's 360 plus 90? 450 plus 90. We're just counting about pi halves. 1 pi halves, 2 pi halves, 3 pi halves, 4 pi halves, 5 pi halves, 6 pi halves, 7 pi halves, 8 pi halves, so on and so forth. There you go. 2 pi is 1 rotation. A half rotation is how many pi? Pi. 1 rotation is 1 pi. Now you know what a radian is. You know what a radian is. It's a ratio of arc length to the radius, and that's why it's unitless. If you've been using, yeah, go ahead and clear your calculator out. We're going to kind of get into it tomorrow with radians pretty heavily. But enjoy the rest of your E-Day, and we'll see y'all back tomorrow.